This is September 2014 Physical Science Paper 2, number 8. I hope that you have your paper in front of you. We look here at the half reaction involving oxalic acid, and that reaction is given with a negative E value, the minus 0.49, and then immediately if you look at your half reaction list, you must see that if it's got a negative value, it will appear on the top part of your half reaction list. That makes it a reducing agent. So that's very significant to notice that right in the beginning. And then they say that the solution of potassium dichromate, K2Cr2O7, that will be a strong oxidizing agent. The moment you see potassium dichromate and potassium permanganate, the KMnO4, always write down that they are strong oxidizing agents. Remember that, because that determines how you approach this question. Then they say, explain why the reaction between the solution of oxalic acid and potassium dichromate will be spontaneous, and they even tell you that you must refer to the relative strengths. Now there's a few things that you can say. First of all, you can say that oxalic acid, the minus 0.49, has a lower E value than the dichromate half reaction, because the dichromate will be found at the bottom here of the table because it's a strong oxidizing agent. So it will have a lower value. You can refer to the fact that because of that, the dichromate ions are therefore the strongest oxidizing agents, and you need a strong reducing agent to react with it. So you will always look at top right and bottom left, and therefore the dichromate will be reduced while oxalic acid is oxidized. You can even do a cell calculation, EMF calculation for this, by referring to your E cell, which is equal to E reduction minus E oxidation, and you do the 1.33 minus the value that they gave you, the 0.49, and that will give you a positive E cell value, which also indicates that it is a spontaneous reaction. Right, in the next question, use half reactions to write down a balanced equation for the reaction, and they say leave it in ionic form. So for that, we always start by writing down our two half reactions. So I will be doing that. So 8.1.2. I like to start with oxidation in reduction. My oxidation reaction will be the reducing agent. So this being a reduction, I will have to turn this reaction around to have my oxidation half reaction. And therefore it's going to be H2C2O4 to CO2 plus 2H plus 2 electrons. And then my reduction, my oxidizing agent, that will be reduced, Cr2O72 minus plus 14H plus 6 electrons. And you just copy this down from your table, plus 7 waters. And then your net reaction. Now first balance your electrons, because the oxalic acid gives away 2 electrons and dichromate receives 6, so you need to balance that by multiplying right through with 3. So it's 3 and 6, 6, 6. Then you cancel out. Now there's hydrogens that can cancel out. So 6 hydrogens there will cancel out with 6 here, and there will be 8 left. All the electrons will cancel out, and there's no waters that can cancel out. So that's it. So then you just add the left-hand side. So it's 3H2C2O4 plus Cr2O72 minus plus 8H plus 6CO2 plus 2 Cr3 plus 7 waters. just to comment about the H+, remember that the H+ always refers to the fact that the solutions were acidified, right? So a little bit of acid was added to the solution. Then number 8.2. Now that was a very important question. A learner sets up a standard electrochemical cell using the following half cells. Now, this is an oxygen half cell with a platinum electrode and H+, meaning that it is also acidified. Then it is forming the H2O2, which is hydrogen peroxide, and then the copper 2 plus to Cu. Now that is a familiar one that you see many times. Now, the potassium chloride KCl solution is used in the salt bridge. So there's your salt bridge. Now, grade 12, the very important thing to do here is always to identify your redox. Before you even start your question, you need to know what is oxidized and what is reduced. Now, I'm going to show you a simple method by which you can determine that. If you don't do that in the beginning, then your whole question can be wrong. So if you take your half reaction list and you work with the two solutions or the oxidizing agent and reducing agent, you need to identify those. Now we know that we've got a copper, which is always the 0.34. So there's my copper. And then the oxygen going to the hydrogen peroxide. Now there's your hydrogen peroxide. Now you simply, I always say, put your finger on the two items on your table and then move the bottom finger so that you have a positive gradient between the two. So always move the bottom one and draw a line, and that will then be your two substances. Now oxygen will in this case be your oxidizing agent, which will be reduced, and copper will be your reducing agent that will be oxidized. So the top one of the two, once you have identified, the top one will always be the reaction that you will have to swap around, because that reaction will lose electrons, will give electrons away for the bottom one. Now we can start to answer the question. Which half cell A or B contains the cathode? Now cathode is always the place where reduction takes place. Now remember that. So reduction in this case will be the bottom one of the two. That is the receiving of electrons. So in which half cell? It must be in half cell B. 8.2.1 is therefore B. Write down the oxidation half reaction. Now again, go to your table. Oxidation half reaction. The reducing agent is oxidized. So as I said earlier, the top reaction of the two will always be the one that you need to swap around. So it's going to be Cu to Cu, 2 plus 2 electrons. Write down the cell notation for this cell. Now the cell notation has a specific format, and that looks like this. It's always the anode first, the oxidation, and salt bridge and reduction. Now, and then it's got the format of, we will fill in the gaps now with these lines. Now please remember that you start with what is oxidized. Now we already said earlier that it is the oxidation half reaction is the copper. So copper will go here, solid, that is oxidized to copper 2 plus, aqueous. Then your salt bridge. Now remember, it is copper that is oxidized to Cu2 plus. Then the next substance. Now you need to write down the substance that is going to be reduced. So what is being reduced here? It is the oxygen. If you look at your half reaction table, it is the oxygen that is going to be reduced to H2O2. So it is oxygen, which is a gas. Now the moment you have a gas and then the next one is a different phase, then you have a solid line. Then it is deacidified, the hydrogen, aqueous, and comma. Now we only put a comma once we have the same phases. If we have the same phases, then you put a comma. If you have different phases, then you put a solid line. And the platinum must also be remembered, because it is a platinum electrode that you have in the oxygen electrode. So I'm just going to go over this again. It is the reducing agent that is oxidized, and then it is the oxidizing agent that is reduced. You put a solid line when you have different phases. You put a comma when you have the same phase. The next question, calculate the potential difference of the cell, the E cell value. Okay, so that will be (8.2.4), the E cell, and please copy this formula exactly like it is on the formula sheet, equals the E cell at the cathode minus the E cell at the anode. You can use any of the three formulas. Cathode, remember, is your reduction. For reduction, we have 0.68, and the oxidation is 0.34 at the anode, and that's 0.34 volts. Then the last question, after several days, the reading on the voltmeter is 0 volt. Explain why this reading is obtained. Now always remember, when a cell reaches 0 volt, then it means that the cell is going flat. There's a few things that you can say. I'm not going to write them down. You can say that the decrease in the V cell occurs when the ions concentration, the product concentration increases and the reactant concentration decreases. You can also say that the rate of the forward reaction decreases while the rate of the reverse reaction increases. Always refer to the rate of and not to just the forward and the reverse reaction. It's a simple reaction rate answer. Thank you. That's all for number 8.